And then, objectives about what we are learning for with this section. So section 7.1. It's mostly review concept. So that's the good news. All right. So just one concept is new to worry at. Okay, but the rest of it are important. Okay. Please. How can I get rid of? There we go. So first of all, one-to-one function. One-to-one function is about the assignment for the function, right? For one value in the domain, you have one value in the range. So it's not like x squared. It's an example of a not one-to-one function. The reason is, okay, 2 in the domain. What happened with its value? 2 squared, 4, right? So 4 gets assigned to 2. But -2, what happened? -2 squared is what? 4 again. So 4 gets assigned to the prefix -2 as well. So you have 2 distinct values in the domain. They are assigned the same output value. So that's not one-to-one assignment, right? You have a -2 to 4. You have a 2 to 4. So that's not one-to-one. Okay, so one-to-one is very easy, like x cubed will be it. You have one value in the domain, you have one value in the range matchup. Okay, so that's one-to-one. What's the advantage of one-to-one, right? So if I draw a simple picture. Okay, so let's say this is 3 values and maybe more, okay? So I call this x of 1, x of 2, x of 3. These are the values in the domain. And then one-to-one, because that means I will have to have 3 distinct values to make the assignment. So this gives you a visual representation, the mapping 1-to-1. Okay, so that will be the range. And this assignment is for F. Okay, so the importance for one-to-one is because we're going to study the inverse function. So it's like reverse assignment. Okay, so what does that mean? Visually, that means, okay, so this time I'm gonna pick y1, make the assignment x1. It's like the reverse assignment. Okay. So based on the F, the rule for F, I define the reverse assignment according to the assignment for F. And this function, that's why it's called F inverse. It's the reverse assignment based on the rule of F. And I do the assignment. Okay, so it's that's why it's you have the pairs, right? You have F and F inverse. This is not inverse of anything else but the F. Right? Because how you make the assignment is based on the rule of F. Okay, so if 1 gets assigned to 3, the reverse image will be 3 gets assigned to 1. It's not like 3 gets assigned to -2 or something like that. You don't get the free assignment. It has to be based on the assignment for F, but you reverse it. Okay, so you have F inverse. And the only way you can get F inverse if the assignment is one-to-one. Okay, let's just do one example, right? What if it's not one-to-one? Okay, so I have, let's just do the x squared as an example, right? So I have 2 gets assigned to 4. Then I have -2 gets assigned to, sorry, that's assigned to 4 as well. Okay, so I call this function g, and g is not 1-to-1. Okay, so what's happening now? I said, okay, do a reverse assignment. Reverse the rule. You're in trouble. You're asked like, which way should I go? It's like you have a fork now. So the 4 gets assigned to 2, or the 4 gets assigned to -2. Right, so that's why 1-to-1 is so important. Okay, but we all know, like, loosely speaking, we know square root of x, isn't that inverse of the square function? What do you say?
Well, it's only fine for like a positive.
Yeah,
Or not negative.
you have to cut it down. That's a -2. Sorry, the spring is not that here. It's not. So you have to cut down the domain, specify additional rule so that you know exactly how to assign the value. Okay. All right. So I do have a question here. So if you have a continuous function, okay, and then you have 3 values, x1, x2, x3. They're all distinct values. And I'm not sure if I have a typo here. Yeah, I think this worksheet I sent to the printer and then I realized I forgot to type in this condition. Okay, so please add it. So x1 is less than x2 is less than x3. Oh, by the way, I do have allergy, so sometimes I cough a little or something because my throat is funny. But it's not like having a cold or anything, but if I do have a cold or something, I will wear a mask. So I want to make it clear. Okay. So please add in this condition. Okay. Okay. So f is 1-to-1 and continuous, and then we have 3 distinct values, x1, x2, x3 in the domain. x1 is smaller than x2, x2 is smaller than x3. Okay, so what's going to happen to the values? F of x1, f of x2, f of x3.
I'll get small.
How do you line them up?
Okay. 3, 2, 1.
What can happen? Okay, so remember, continuity is important. It's not like discrete. Okay, so you pick x1, you have f of x1. The first one is almost like free, right? But continuity, okay? So x2 is a bigger one. Where can it go for f of x, x of 2? So 1-to-1 says what? These two cannot be equal. Because otherwise it's not 1-to-1, right? So 2 map to 4, -2 map to 4, that's no good. Okay, so that means f of x of 2 has to be either bigger than f of x of 1 or smaller than f of x of 1. You do have a choice at this point. Bigger or smaller. Okay, let's first assume it's bigger. Okay, f of x of 1, f of x of 2. We have f of x of 2 is bigger than f. Where can f of x of 3 go? Remember, it's continuity.
Low.
Can it be lower?
Has to be shaded in sub 2.
If it's lower because of continuity, you won't pass the horizontal line test. You won't get a 1-to-1 function. Because anything in between, we already assigned. So if this one goes down, you won't pass the horizontal line test. So it has to go up. Okay, but if f of x of two is smaller than f of sub one, what happened to f of x of three? Then it's small. Okay, so one way or the other, the continuity plays an important. Okay, because it's not discrete. So two important part. Continuous. 1 to 1. Okay. Two conditions. So that means you can have two output. Sorry, wait a minute, I put it here. One output. You can have this outcome. Or you can have the other outcome, one or the other. Okay, but you can't zigzag in it because of continuity. Okay, so that's why if you have a continuous one-to-one function, it has to be either increasing or decreasing. Okay, and then to determine what is one-to-one, and we have a horizontal line test if we have the graph of the function. But remember, for graph of the function, a lot of times we can only view that window that's given, right? So if you don't have the knowledge of the entire graph, the horizontal line is not the best way to go because you don't know what's happening to the function outside that window, display window, right? But it's a way to do. But somehow you gotta know the behavior of the function a little bit. Okay, and then derivative of the function, can we do it? Anything in calculus 1 that you learned? Will help at this point?
Critical points.
Critical point, almost there. Interval increase, interval decrease, how do you determine that?
First derivative test.
First derivative test. So you are able to use derivative to test whether or not function is increasing or decreasing, and then determine whether or not it's one-to-one. Right, if it's strictly increasing, it has to be one-to-one because it's not exactly. If it's strictly decreasing, it is one-to-one because it's not exactly. Right, there's no repeated value there. Okay, so the derivative can do. And of course, some of you eventually will deal with proof problems, and it's a little bit more abstract. For harder questions, you can approach using that the definition, of course. Definition will always be. All right, so all of this can be, all of this can be. But it's up to you to decide when to use which one. To determine, all right? Okay, so let's apply some of these concepts that we just talked about. This time, we need to determine this function is one-to-one, right? So the challenge here that if we do not have a graphing utility, we know the behavior of the x function. But cosine function is a wave, right? It's not one-to-one. So without visually seeing the behavior of the function, just ask you to determine if this is one-to-one. It's not like immediate answer. Okay, but let's do. But we do know the function is continuous, right? So let's do the derivative, right? Say, what's f prime of x?
1.
1 plus or minus, what's derivative of
Negative.
negative psi also? All right, sine function, what's the range for sine function? The smallest value is -1, the highest value is 1. So it's between -1 and 1. So what can you think about this? Positive value, negative value, or what? What's the biggest value you are subtracting here? What? So it's always gonna be greater than or equal to 0. Since the range of sine function is between -1 and 1. So can we tell it is a one-to-one function at this point? Not right away, because greater than or equal to 0 doesn't tell us function is increasing or decreasing right away, right? The ideal condition is strictly greater than 0 or strictly less than. Right? But what do we have? F prime of x is equal to 0 only when sine x is 1. Okay, the time when the derivatives is equal to 0 is when sine x is equal to 1, but when is sine x equal to 1? Sine of what is 1? Pi over 2. And sine, the period of sine function is? What's the period of sine function? For a full wave. 2 pi, good. So remember, this is the notation. Plus 2k pi, that's the complete solution. Right, because every 2 pi, you will get an answer that sine x is 1. Okay. So that means what? That means the derivative is equal to 0 is not on an interval. It's only on isolated point. Every 2 pi you get a 0. Okay. So it's only for isolated points. And so think about x cubed function. And what's the derivative of x cubed? 3x squared. And this is what, greater than equal to 0, right? And where is it equal to 0?
0.
At the 0. So look, this is, sorry. This is not the x, it's good. So what's happening here is this cube function has a horizontal tangent line there at 0. Okay, but we still say x cubed is an increasing function. Because if it's 0, it gives you just that horizontal tangent line, right? So this situation, this function has that situation infinitely many times. Get a horizontal tangent line every 2 pi. Okay, but function keeps going up and up. Okay, so I think the graph will look something like that, going up and going up. So you kind of get that. That should be a little bit more. Get a horizontal tangent there. Right, so you get a horizontal tangent there, so, and then get another horizontal tangent there. So it's something like that. Every 2 pi you get a horizontal tangent. The function is still increasing, right? increasing on its domain. As it's 1 to 1. Does it make sense? But it does use quite a bit of concept to be put together to justify this one, right? See, that's another reason why Calc 2 can be hard, because it really use a lot of concept, integrate together, maybe to solve one problem. Right? Okay, so for those of you came in late, I am trying out something new this semester, because I'm on Zoom and I'm recording this lecture. Just in case you have to leave early or late, so you can always go back and check the recording and make things up. Okay, and I also provide the worksheet, so I will start posting the worksheet on our pool. For those of you coming in late, do you need me to print out, or you prefer the digital one? Download it and take it on your iPad or something. You print it?
Yep.
You want me to go? So I will not print out one for you then. Just trying to save paper, right? Okay, all right. Okay, so theorem. Existence of inverse functions, right? So if f is 1 to 1 on its domain and R is the range, then f has a unique inverse, and the notation is f inverse, right? Is the -1 over there. But it's reversed, right? See, the domain is R, which is the range of f, right? The range for f inverse is the domain for f. Which makes sense, right? Remember this picture? We reverse the assignment. So with respect to f inverse, this will be the domain for f inverse, and this will be the range for f inverse. So the domain for f inverse is really the range for f, right? So that makes sense. This is the reverse assignment, right? And then we do have this cancellation formulas. It gets canceled. Okay, so let me draw a picture. This time I only have one value to show. So let me just put x of 1 here. And then this is y sub 1. Okay, going this way, call it f. So that's domain for f, that's range for f. Okay. And the reverse going this way. So I call this reverse assignment f inverse. So then this is domain with respect to f inverse, and this is range for f inverse. Okay, so think about it. The first cancellation formula, you start with f, okay? So you start with x of 1. F of x of 1 gave you the value y sub 1. Oh, I got the time. Okay. And then f inverse of y sub 1 is assigned back to x sub 1. Okay, so that's why you have this cancellation formula. But if you start with f inverse, so if you start here, y sub 1, f of inverse, f inverse of y sub 1 give you the value of x sub 1. Then f of that will give you back y sub 1. So that's the other cancellation formula. Okay, but this 1 to 1 is important, right? So you know exactly how it's assigned. And then a practical example to think about it, since a lot of you will take chemistry and the physics, is the conversion between the two types of degrees, the Celsius and the Fahrenheit. You have a conversion formula. You have it from Celsius to Fahrenheit, then you have it from Fahrenheit to Celsius, and they are inverse of each. And those are one-to-one function. Okay, so that's a practical example to help you understand the inverse and the assignment and so on and so forth. And graph of F and F inverse, because of the reverse assignment, right? So they are symmetric with the line y is equal to x. So this is one example. So I have x cubed here, and its inverse is cube root of x. So you can see this. Sorry, it's not colored print for your worksheet. I can only get free print if it's black and white. But at least you can see here, right? This blue one is the cube root of x, and this red one is x cubed. And this line here, so their image, they're symmetric with respect to that. Okay, and the reverse assignment, you can tell for x cubed, 2 cubed is 8. But then reverse, for cube root of x, you have cube root of 8 is 2, right? So they get flipped, right? So these are familiar concept for you, right? It's a good review. Okay, all right. Right. All right, let's look at exercise 3 here. True or false? We have square root of x is the inverse of x squared. Well, we talked about this early on. True or false? Is okay. What we have been talking about, 1-to-1, the assignment, inverse has to be what? The reverse assignment. X squared, is it 1-to-1? How do you reverse the assignment if I don't make some special condition to it? 4 gets assigned to what? 2 or -2? Right, if I don't put any restriction, you tell me, I don't know. Okay, what happened to square root of x? 4 gets assigned to what? 2. Okay, so square root of x, so this is not true, okay? So pay attention, f of x
So we'll make it true.
is not 1-to-1. Yeah, I'm waiting for your question. That's an excellent question. Why is it true, right?
Yeah.
Yeah, we kind of always say square root is the inverse of x squared, right? So that's loosely speaking. Where's the understanding? Okay. Square root of x is the inverse of restricted x squared function. Okay. So I make f of x to be x squared. And the domain I cut it down to just half. So 1 squared is 1, 2 squared is 4, 3 squared is 9. So when you go reverse, 9 square root of 9 is what? 3 square root of 4 is what? 2. So that's how you get the inverse. Right, and this is something I'm using this familiar function to help you to see that if a function is not 1-to-1, but if we're adding in special condition, we still can kind of make the inverse out of it, but not out of the entire function. It's out of a portion of the original function, right? That will help us understand later on section 7.5 about inverse trig functions. It's kind of like putting in additional condition to make it happen. Right, so this one is easier for you to see, and keep this example in your head. When we talk about inverse trig functions, it will help you to get what's going on, right? What about cube root and x cube? So they are inverse of each other, okay? So I want to emphasize here that f is the inverse of F inverse. So F inverse is F. So that's why when you get an inverse, it's a pair. They're inverse of what? Each other. Okay. So the inverse of F inverse is actually F. Okay. What about the last one?
Oh.
What did we learn from this example?
The four, five, the things.
Right. See, that's why it's not about how many examples I gave. It's about how much you can get out of each example. So hopefully everybody will choose what?
So
And the reason,
the two, anything that's even gonna come to a positive, but you can use negative.
is this one-to-one function? Did I put any additional condition to restrict it? No. So that means it's everything. If it's everything, it's not one-to-one. There's no inverse to it, period. So for the same reason. Right, so this is a good example. What did we learn from this one? You can't have inverse if your function is not one-to-one. Because you can't make the assignment, you cannot reverse the assignment. Okay, so if you get this one, same concept, just apply to a different function. Okay, and this is how you study. It's not about how many examples I let you try. It's about you learn something from the example and later on you can apply that concept when you work on other problems. See, same concept, right? Just a different function. Okay. And this is super important because otherwise I give you 10 examples in class, you will tell me, you never did this one in class. I can't do the quiz. Okay, if I ask you to work on a quiz problem, that means that I have covered the concept. It's about applying the concept, all right? Okay, but sometimes it is hard. Okay, I'm not saying that's easy. So if you have trouble, what do? You can talk to me. All right, so don't wait because it goes so fast, you don't wanna wait.
Well, it says that, what h of x is the inverse of k of x, and k of x has the domain of negative, numbers, right? Or, I mean, not positive, right?
See, again, if it's inverse of each other, both functions have to be one-to-one. So this one, we have to cut it down as well.
Isn't the domain already cut down though, because we're originally dealing with the fourth root x? Which.
No. It's not the entire function. Because I didn't give you the restriction for this one. It's like, I cannot say x squared is the inverse of square root of x. Same thing. Which is the inverse of square root of x? It's this one plus this condition. And I didn't give you that extra condition here, so the entire function is not one-to-one. It cannot be the inverse of a one-to-one function. Okay, remember, it's inverse of each other. So when I say this is the inverse of this one, which means I say this is the inverse of this one as well.
Okay, that makes sense, thank you.
Okay, it's a pair. It's a pair. But good questions though. Okay, do ask questions if you have. Are we good here? Okay. Okay, finding inverse function. It's something we did before. You can solve for x first. Make your restrictions if needed, and then you interchange the x and y. Okay. Some textbook will say interchange x and y first and then solve for it, but pretty much the same. It doesn't really matter. Okay. So let's practice one. states, domain, and range, right? Okay, so, let's make y to be equal to square root of x plus 2 minus 1. So remember, we gotta solve for x. So square root of x plus 2 is y plus 1. And then we square on both sides. So we get x plus 2 is y plus 1 quantity squared. And then solve for x, subtract 2 on both sides. Okay. All right, notice that we started with a function 1 to 1. We ended up with a function not 1 to 1, because that's a parabola, right? So that means, let's do one more. Okay, we gotta interchange y and x, so that means we want to write f inverse of x is x plus 1 squared minus 2. But notice I put comma. It's not done yet. Okay, so if I don't put extra condition, it's not matching up. You have a 1 to 1 function, you ended up the inverse is not 1 to 1 function. Okay, so same as x squared, you have to find which branch is actually the inverse of it. Okay, so if you have graphing utility, you know the vertex, and you just have to pick up the correct branch. But otherwise, remember the domain of the inverse is the range of f, right? So what's the range of f? Well, square root has to be what? Greater than or equal to 0. You subtract 1 to it, so that means the image has always gonna be greater than or equal to -1. And that's the range for so it's this plus this condition tells you that is the inverse. So the domain of f inverse, we're going to figure that out. And the range of f inverse, you can go directly from here or from there. So that has to be the domain of f. But in any case, if you look at this one, when you square something that's greater than or equal to 0, subtract 2, that is greater than or equal to -2. Okay. So I'm using this examples to help you get used to how to get inverse of maybe a function that is not 1 to 1 to begin with. So that means we need to apply some restrictions. And the purpose of practicing this kind of example will help us get the concept when we deal with inverse trig function. Right, so we all know those trig functions, they're periodic functions, so they're not 1 to 1. But we do talk about inverse trig functions. Right, how does that happen? That means we have additional conditions to it. And so the additional conditions are super important because you have to map it right. right? You map it to the right branch or you map it to the left branch. That's separate stories. The rules are not the same. Okay, continuity. So if a function f is continuous on the interval and has inverse, so that means it's one-to-one, continuous on the interval I. So that means the inverse is also continuous on the interval consisting of the points f of x, where all x in the initial domain for f. So the inverse is also continuity. So continuity map to continuity. All right. Okay. Before we move on to the next topic, are we good so far? Because all the way up to here is like review some of the one-to-one concept and so on. All right. Mark this one, and that's the only new concept for this section. So that one is new. It's called the derivative of the inverse function. So f is differentiable and have an inverse on an interval I. So see, that's important, right? Have interval I, so which means it doesn't require one-to-one on the domain. Right, as long as it has an inverse on an interval I, which means one-to-one on a certain interval will do. So it's like all those trig functions, you restrict on the interval, you get the inverse, and that will work as well. So we start with one point x of 0. And the derivative at that point is not 0. Why? Because we're taking the reciprocal of that value, so it doesn't make sense we divide by 0. So it tells you how to get f inverse, the derivative of f inverse of y sub 0. And what is y sub 0? Y sub 0 is the image of x sub 0 in the f. Uh, Sorry, this should be y sub 0. No, x sub 0, sorry, x sub 0. I missed the 0 there. Okay, so what's f of x sub 0? Y sub 0. Okay, so let's draw it out. X sub 0 gets mapped to y sub 0 under f. Okay. And y sub 0 mapped to x sub 0 under f inverse. So f of x sub 0 is y sub 0. F inverse of y sub 0 is x sub 0. Okay, so let's practice this. So if f is x cubed, how do we find the f inverse prime of 8? Right? So there are two ways to do it because we know how to get the inverse of this one right away. Okay, so let's do it directly. So I call this one method number 1. So if you know the inverse right away, you don't have to go through that fancy formula because that can be confusing. Right? So what's F inverse? This one we know very well. Cube root of X. And then we just differentiate that. Derivative of F inverse. We use the power rule. Right. So that's 1/3 times cube root of X squared. And then let's evaluate. So derivative of F inverse at 8. So you plug in and do it. I think it's 1/12. So if you know the inverse right away, you don't have to go through that hoop to get it. Okay, but to help you get familiar with this new derivative formula, so what if you can't get the inverse easily? Okay, that's the way to go, right? So let me do measures for 2, use the new formula to do it. What does that mean? Right. All right, so this is what you look at. 8 is what? Is the y naught in the formula. Okay, so what's its pre-image? What cubed will give you 8? 2. Okay, the 2 is equivalent to the x naught in the formula. Okay, so what does the formula tell you to do? Well, you gotta look at f prime of x naught. Okay, so let's do f prime. F prime of x is 3x squared. So f prime of what? Not 8, but 2 is 3 times 2 squared is 4. Okay, so f inverse prime of 8 is 1/f prime of 2. So that's applying the formula. And that's 1/4. Okay, so if you know the derivative, if you know the inverse right away, don't have to use this new formula. This is like a long way to get the answer. But it's extremely useful like doing the next problem. What is the inverse of x plus cosine x? We know it's increasing. It's 1/1. It has an inverse, but who wants to solve for it? I don't. Okay, in cases like this, the new formula is extremely helpful because you don't have to get the f inverse, but you are able to get the derivative, the information of derivative of f. Okay, so that's why I'm doing this one. This is something you're familiar with to help you connect with the formula, right? Which part means y naught in the formula, which part means the x naught in the formula. All right, so for this one B, we don't have to find the inverse. Okay, I can get the inverse explicitly, easily. So I don't solve for it. Okay, I don't go around it. Okay. So this y1 here. Okay, so this is the y naught. Okay, I try to map with the formula here. Okay, this is the y naught, like in the formula. So the question you have to answer is f of what is 1? Okay, so usually for problems like this, when it's harder to find the f inverse, they don't give you something impossible to get. Okay, they give you something actually easy to find. You can try some nice values and figure it out. Okay, f of one, cosine. So first of all, cosine has to have a nice value, right? Because otherwise you get the root or you don't even know how to get it. So it has to have, so you want to think about special values, right? Cosine of 0 is what? So usually for this kind of problem, you think of some nice values to try, and usually it's easy for you to find the value. Okay, don't solve for it, because it's hard. F of 0 is 1, and this 0 is like what? 0 is like the x naught in the formula. Okay. All right, so let's continue. What do? We do f prime. And we did that before. That's 1 minus sine x. Okay, and then we do f prime of x naught. So that means we do f prime of 0. So that's 1 minus sine of 0. What's sine of 0? 0. And then we do what we are asked to find. The derivative of f inverse at 1 is 1 over the derivative of f at 0, which is 1 over 1. It has the same value in this case. Okay, so I emphasize, if you know the inverse, go directly, because that's easy. That's the shortcut. That's the easiest way to do. But if you can't get the inverse easily, use the formula to go around it. And again, you don't have to solve for inverse, because if you're able to solve for inverse, you can go directly, right? So the formula is useful is when the inverse is hard to find or impossible to describe easily. And the pre-image usually is easy to find because they just want to give you an opportunity to apply the concept. They wouldn't give you something impossible to get. Okay. All right. So this is the last example on this. Okay, the reason I'm doing this again is to set up that you're getting used to the concept where sometimes you don't have a one-to-one function, but when you cut down the domain, you are able to establish a one-to-one and then inverse of that. Okay, and you gotta do the correct mapping, right? It's super important later on when we do the trig function. All right, we need to find the derivative of f inverse of -6. Okay, and this f. All right, what trouble do we have? F is what? 7-degree polynomial means it is parabola, which means it's not one-to-one. Trouble. Okay, but it is one-to-one when we restrict the domain. So we restrict it to one piece. Remember, this is open up, so you have a parabola like this again. You wanna have the piece where x is greater than -2, so the right-hand side piece, not the left-hand side piece. There are 2 ways to do it. One way, you find its inverse. Anybody want to find the inverse of this one? It's possible, but it's not an easy task. Why? The easiest way, you gotta complete the square and then solve. And I don't think you really like that process, completing the square. Another way is to use the formula to go around it. So we don't have to find f inverse, we deal with f directly. Okay, so let's try to deal with the f directly, avoiding that completing the square part. All right. So we gotta find the pre-image, right? So we're gonna set it to -6, And we try to solve for the pre-image, right? The answer, the question f of what is -6? So we have x squared plus 4x and plus 3. Okay, we're gonna add 6 on both sides. This one we can factor easily. So x plus 1 and then x plus 3. So we got two solutions. X is -1 or x is -3. Okay, which one is the one that we want?
Yeah, negative.
Yeah,
Negative one.
Right, so,
Negative two, negative.
right, so that means, in our case, f of -1 is -6. Right? Since. So you gotta pick the right one. See, picking the right one is super important. So I have emphasized several times today, is to set up for, learning the trade and the inverse trade fund. So that's why it's super important to remember how we restrict them, so that we can pick the right answer. And then, okay, so now we found the pre-image, the rest is routine, right? I gotta add time. So x plus 4, f5 of, -1. Okay, so this is your x naught. Okay, and then the last one to apply the formula. That's 1/f5 of -1, so that's 1/2. Make sense? Questions? Okay, all of these, the last one is the most important one, because that's the new concept for Calc 2. That means when we do tests, what's gonna be tested from this section? That's this last one. All the previous ones, they are, reviewed to set it up. And those are important concepts because they're extremely important when we deal with trig functions. And you have questions, any questions?
So in the actual, your trig function, like in my last class, we was able to use the table. As far as we figure out sine, cosine, and cosecant and all that, are we still allowed to use the table on the test? No, we have to memorize that.
You do have a cheat sheet.
Okay, thank you.
Yeah, some of you, came in late for the exams, you gotta do outside the class time. I put it on my phone. So that means it's open book, open notes.
Oh, thank you.
Okay, but, you gotta have, I recommend you have the cheat sheet ready.
Yeah,
Because time is precious, right? You wanna use the time to solve the problem, not use time to look up for formulas.
thank you, Dr. Garcia.
Do we have to submit the scratch paper?
Yeah. As long as you present your work step by step,
Yeah.
and that's okay.
This one.
On Pearson.
Alright, so see, for example, here, some of the questions are easy, some of the stuff that I didn't skip, I showed the process how I went there.
Yeah.
Because if you,
Just, when they said.
like this one. I cross this one out, I claim f of -1 is -6. Why do I cross this one out? This is the reason. Because that's how we restrict it. Right, so remember, only when you write on paper, I know what's going on. Right, if it happened in your head, it's not on paper, then I don't know you process that information. So you wanna make sure your solution is reader friendly. Right, I can see how you process information, how you solve it. If you process in your head, I don't know because it's not on paper. So the good news about L2 is we start kind of slow in the sense that the first 3 sections, a lot of review material, well, actually the first 4. Lost the connection. I might have to see if I have the Wi-Fi connection for my iPad. That could be it. All right, section 7.2 is about ln x and e to x. And its derivatives and the integration formula is related to these 2 formulas. Okay, in the pre-calculus, I believe most of the textbook will define e to the x first and then define ln x as inverse of e to the x. Okay, but in this case, we define ln x first and define e to the x as the inverse of ln x. Okay. See, a lot of stuff we established before, we have like assumptions on it because we were not able to define it precisely. But now, some of these we can redefine it in a precise way, right? Okay, that's a good also review for what we learned, connect what we learned from Cal 1. So I didn't just tell you that's the definition. I actually is gonna go over it carefully, right? This is the official definition of ln x. It is the definite integral for 1 over t from 1 to x. So, and this is the domain, right? Because that's our definition, defined for all x greater than 0, so that means that's the domain for ln x. And we're gonna review the fundamental theorem of calculus part 1. If f is continuous on a closed interval from a to b, so remember this area function, right? So we have the area function, which is defined as the definite integral of f from a to x. It's also continuous on this closed interval from a to b. On top of that, it is differentiable on the open interval from a to b. And the area function satisfy the derivative of this area function is really the integrand, is f of x. Okay. All right, so we're gonna apply this concept, how to differentiate a function like this, and also the concept of area function. So let's go through this. So the domain of ln of x, as I mentioned, based on the definition, is all x that is greater than 0. The value of ln of x represents, so remember the area function? Okay. Let me ask you, what is the geometric interpretation of this definite integral?
Straight over B. Okay.
Right, for a definite integral, the answer is a number. What does that number represent?
Area under the curve.
Close. Not just the area, but what area in the net. Okay, net area. So based on the definition, ln of x represents the net area bounded by this function 1 over t and the t-axis from, okay, so the lower limit for that is 1. So that means from 1 to x, the stopping point. And by the properties of this definition, right, definite integral, so ln of x is going to be greater than 0 if x is greater than 1. Equal to 0 if x is equal to 1, because your lower limit and the upper limit, they are the same, so you don't have any area. Okay, and it's going to be less than 0 if x is between 0 and 1, strictly between 0 and 1. So these are the facts that you know, right, based on the previous knowledge, but now we are looking at in terms of calculus, and why these are true, right? And also the meaning of your, the values for any, element of anything, right? They actually represent the net area. Okay, by the fundamental theorem of calculus 1, we can differentiate this. So what's the derivative of ln of x? This is new, right? We didn't learn this in Cal 1, but applying this theorem that we learned from Cal 1, can you tell me what is derivative of ln x? 1 over x. 1 over x. For all x in the domain. Okay, remember the domain is everything positive. And so that means if everything positive, what's happening to the derivative? Is greater than 0. And if derivative is greater than 0, based on Cal 1, it tells you that ln x is strictly increasing or decreasing. First derivative test. Increasing. Okay, so differentiate again, second derivative of ln of x, right? So what's the derivative of 1 over x? Well, you can do it in your head, or you can do it on the paper on the side. What's the derivative of 1 over x?
X to the level 1, x negative 2.
What's the power of the rule? That's the second derivative, is always gonna be what? Less than 0. So ln of x is what? Concave up or concave down? Down. Okay, what's the shape of increasing concave down? Increasing concave down. Okay. So I've been telling my Cal 1 student, concave up. And one is increasing, one is decreasing. Concave down, one is increasing, one is concave, decreasing, right? Increasing concave down is decreasing. So now you know why the graph of LMX looks like that. It all makes sense, right? Okay, now we try to derive the chain rule for differentiate that. Let's recall the chain rule formula. So let's use the notation that we used before. So the big F is composite function of f and g, right? The little f of g. So f prime of x, the big F, right? The derivative of big F function is f prime of. And we have to make a substitution, f prime of g of x. Times, that's a multiplication. G prime of x. So let's try to match this up. So it helps us to apply the chain rule, right? So that f of x, the big F, to be ln of g of x. And we call ln the little f function. All right, what's the derivative of ln? Remember? 1 over x. Okay, I gave you a minute, see if you're able to derive it by yourself using the chain rule formula. Try your best. See if you can basically just apply the chain rule. Well, we memorize the chain rule, but more importantly, you need to know how to apply it. That's very. See, I usually don't, well, before COVID at least, it's always closed book test. It's always in class test for my Cal 1 student. Those formulas are really fundamental and the foundation that happens. So it's like you don't want to do, what's 2 times 5, and without calculator, you don't know. Right, that will take you forever to finish your homework. But once past Cal 1, I always allow cheat sheet before. I mean, before COVID, most classes are face-to-face in. Okay, because once you know the foundation, those essential formulas, the rest is about application. Okay, so again, it's about applying the chain formula. What do we know? We have to figure out f prime, right? So let's do it. What's f prime in this case? Derivative ln of x is 1 over x. That's the new one we just learned. Then we have to do a substitution because we know we have to get f prime of g of x. So f prime of g of x in this case is what? Exactly. Okay, and we're done. Derivative of ln of g of x is f prime of g of x times g prime of x. The shorthand is G prime over G, basically. And it's derived from chain rule. So this is a more useful formula. Because most of the time you will differentiate just the ln x is ln of something else, a composite function. Okay, so that's the chain rule version for it. Okay, so let's do one more example here. All right, we practice this formula right away, all right, for something simple. Let's differentiate this function, ln of xy, x is positive. Let's first assume y this is a positive constant, because it's connect with the next, right? Okay, so f prime of x based on the formula, see, it's not ln of x, right? If it's not ln of x, chain rule. Okay, so that's the derivative of xy over xy, because that's just g prime over g. Okay, what's the derivative of ln of x? It's just x, ln of x, that's 1 over x. Anything else, chain rule. And since y is a constant, what's the derivative of xy?
That's one.
What? Because y is a constant, it's like 2x. When you differentiate, you keep the 2, the derivative of x is 1, right? Okay, y is a positive constant, so make sure it's not 0, right? So that's fine. Interesting. It is also 1 over x. Okay, anything learned from count 1 will tell you about ln of xy versus ln in this case. Okay, so when you do indefinite integral, you always have to write what at the end? The big C. Why the big C?
Because it definitely is always
What's the root of a constant C? Any constant? What's the derivative of any constant? Derivative of a constant is 0. Right, so you can have a whole bunch of functions. If they differ by just constant, they're gonna have the same derivative. So that's why when you do indefinite integral, you always have to get plus C, because you don't know which one. Okay, so that tells you, right, that ln x and ln xy, in this case, y is positive constant, are all by a constant. So for the next one, because for any positive y, because they have the same derivative, they off by a constant. Okay, but let's figure out what the constant is, right? Let x be equal to 1. So we have on the left hand side, ln of 1 times y, which is ln of y, has to be equal to the right hand side, ln of 1 plus c, and what's ln of 1? 0. So the c is what? Ln of y. So I'm going to use the next few examples also help us to review some of the properties for Allen function. Okay, and also some of the concept that we learned before. But I think I will stop it here. Do we have time? Oh, so we do have 5 minutes, sorry. The clock is off a little bit. Okay. Let's do this easy one first. Let's do the H first. And because I want to use the opportunity to review the fundamental theorem of calculus a little bit. Because we talked about it, but I didn't draw the picture for it. Okay, so let me draw a picture for it. And notice that I didn't use x-axis, I used t-axis. And the graph that we're gonna have here is 1/t. Okay, so the net area here. Okay, so based on the definition of ln of 2. And then, let me show that. The area of this region right now I'm shading is based on the definition of ln of 2. So that's based on its definition, right? Ln of 2. And what's 1/2? This portion. The area of this rectangle. That's the value 1/2. So you can see that ln of 2 has a value that's greater than 1/2. So I want to use this opportunity to also review the fundamental theorem of calculus, the area function parts, as well as the geometric interpretation of definite integral is the net area. Okay, let's see. So,